Good day, dear students. In this video we shall see about the basic idea behind global stiffness matrix, how two or more elements can be added to get the global stiffness matrix, the properties of the stiffness matrix, details pertaining to stiffness matrix, how to add up two or more stiffness matrices, analysis of truss element, what do you mean by a truss, examples, and how analysis for the truss element can be done. Next, elemental stiffness matrix when it is an for a plane stress element will also be derived in this video. So the elemental stiffness matrix for a truss element also will be seen in this video. The basic derivation will be covered in this video. So here you can see an example for a element. So this is a structural system. It is having two elements of length L1 and L2 and cross-sectional area A1, A2, modulus of elasticity E1 and E2. So a structural system, whenever we are considering, it is an assemblage of number of elements. It will not be of a single element. It will have multiple elements, two or more elements. So these elements are interconnected together to form the whole structure. Therefore, the elemental stiffness matrix of all elements are first needed to be calculated, and then they have to be assembled in a systematic manner in order to obtain a overall or global stiffness matrix. So the global stiffness matrix is an assembly of all elemental stiffness matrices in a systematic manner. Let us consider an example as shown in the figure here. So we have a stepped bar. It is fixed at one end and subjected to load F at other end. So the stepped bar can be modeled as finite element model by using two 1D bar elements as shown in the figure 4.1. So this stepped bar has multiple properties, that is cross-sectional area A1 at the top and cross-sectional area A2 at the bottom. Similarly, modulus of elasticity is E1 and E2. Length is L1 and L2. So all the properties are different. A, E and L are different at different locations. So two elements are coming together to form a single structure. So let us see how the elemental stiffness matrix for this bar element can be derived and how it can be assembled. We'll move to the next slide. So here you can see the formula for the stiffness matrix is nothing but AE divided by L, 1 minus 1 minus 1 1. So where AE is nothing but the area of the element, capital E suffix small e is the modulus of elasticity of that particular element. L suffix E is nothing but the length of that particular element. So for the first element, K suffix 1 will be equal to A suffix 1 E suffix 1 divided by L suffix 1 into 1 minus 1 minus 1 1. You can observe here I have written 1 with the small letter 1 on the top and small letter 1 on the right side. You can just observe here I have written 1. Similarly, for the element 2, K suffix 2 is nothing but A suffix 2 E suffix 2 divided by L suffix 2 into 1 minus 1 minus 1 1. So here the 1 represents the node 2 and the first column, first row, value 1 represents the node 2. Similarly, the second column row 1 represents the third node and the effect on the second node. Okay, so here we can see 2 and 3 is written on the top and on the right hand side. So effect of node 1 is represent on the effect of node 2 is represented in the first stiffness matrix, whereas the effect of node 2 and 3 is represented in the second stiffness matrix. Now when I am adding the two elemental stiffness matrix, I will have to add K1 and K2. So here A E divided by L for element 1 will go inside. So for the first row, everything is similar to the variables in the element 1, whereas when it comes to the node 2 and 2, effect of node 2 on 2, it is there in both the matrices. So I will have to add it up, A1 E1 divided by L1 plus A2 E2 divided by L2. So you can observe only at the node 2 the adding up happens, whereas at all other places it is just the values that is there in the either of the elemental stiffness matrices. Only at node 2 the adding up happens. Only at the node 2 the adding up happens. So whenever we are speaking about the stiffness matrix, the stiffness matrix has certain inherent properties. So these are with respect to the property of the structure. So the primary characteristic of a finite element are embodied in the elemental stiffness matrix. So all the properties or characteristics of the structure is by default inbuilt in the stiffness matrix. So the element stiffness is obtained with respect to its axis and then transformed this to the stiffness to the structural axis. So for a structural finite element, the stiffness matrix consists of geometric behaviors and material behaviors. You can clearly see that cross-sectional area and length which pertains to the geometry is inbuilt in the elemental stiffness matrix. Similarly, the material behavior, that is modulus of elasticity E, is also inbuilt in the elemental stiffness matrix, which in turn is transformed to the entire structure to get the structural stiffness matrix. So this indicates that the resistance of the element to deformation is because of its geometry and because of its material behavior or material property when it is subjected to loading. So such deformation may include axial bending, shear, torsional effects. So for finite elements used in non-structural analysis like fluid flow, heat transfer, etc., in such problems the term stiffness matrix is also used, but there the stiffness matrix will have different property. It will not have the modulus of elasticity or as an inherent property. In structural problems it is modulus of elasticity that forms the stiffness matrix, but in fluid flow problems, in heat transfer problems, the matrix represents the resistance of the element to change when subjected to external influences. So fluid related properties, heat related properties will be inbuilt in the stiffness matrix. So the properties of the stiffness matrix can be considered as a stiffness matrix is a symmetric matrix. So along the diagonal the values will vary, but along the above the diagonal and below the diagonal the values will be same. So it is a symmetric matrix always. Stiffness matrix is obtained in finite element analysis and it is a banded matrix. If there are n number of nodes, then the global stiffness matrix will be n into 1, n into n. For example, if there are 3 nodes, then the global stiffness matrix will be 3 into 3. If there are 4 nodes, we will have 4 into 4 matrix, provided the element is one dimensional and 1 degree of freedom is there at each node. The main diagonal elements are always positive. the diagonal elements will always be positive. If rigid body motion is not prevented, then the stiffness matrix becomes singular, and sufficient boundary conditions has to be applied to remove the singularity. So these are some of the properties of the element stiffness matrix. So once again, let me tell you, the stiffness matrix is like a password for a particular structure. If you are able to crack it, you are able to solve the particular problem. So next topic is truss. So truss is an engineering structure that is considered to be consisting of slender members, and they are connected to the adjoint member at their ends only by means of welded joints or by bolts, rivets, pins, etc. And they have a closed geometrical configuration. So a typical plain truss is shown in the figure. So plain trusses are defined as truss whose members lie in a single plane. So common assumptions usually made in analysis of trusses can be discussed in the next slide. So here you can see simple trusses. So you have through Pratt truss, Warren truss, Deck Pratt truss, Parker truss, Howe truss. These are examples for the truss structure. So a plane truss is defined as a truss whose members lie in a single plane. So the assumptions are member of truss are connected at their ends by frictionless pins. Truss is loaded and supported only at its joints. Forces developed within the members of the truss are purely axial and no bending is considered. So weights are assumed to be applied at the joints. Half the weight of each member is applied to the two connecting joints of the member. So from the assumptions, that is very clear that each member of the truss can now be treated as a two force member, that is, it is loaded by two equal and opposite collinear forces, and with entire truss considered to be a group of pins and two force members as shown in the previous slide. So the finite element method is applicable to statically determinate as well as indeterminate trusses. So finite element method can compute joint displacements, member forces and member stresses in the truss. So analysis of a truss is of a very vital importance as they offer practical solution to many structural problems in engineering such as bridges, roofs, buildings, cranes, transmission towers, etc. So a two force member under tension or pull is shown here, and two force member in compression or push is also shown at the bottom of this slide. In the next slide, let us derive the equation for the stiffness matrix of the truss element. So if we observe the stiffness matrix, figure shows a typical plane truss element in local and global coordinate system. So the local coordinate system consists of x-axis which runs along the element from node 1 towards the node 2. So here it is clearly visible that the orientation of local coordinate axis changes with the elemental orientation, whereas the global coordinate system is fixed and it will not depend on the orientation of each single element. So let us consider x and y to be the global coordinates, and in global coordinate system every node has 2 degrees of freedom, that is along the x-axis and along the y-axis, the linear motion along the x-axis and linear motion along the y-axis. Hence a systematic numbering scheme has to be adopted. So if we consider an example, if the global node number is j and it is associated degree of freedom is q 2j minus 1 and q 2j in x and y direction respectively, as shown in the figure below. So here you can see a simple plane truss element. So then I am taking it to the local coordinate system, giving it the angular values of theta, then finding out the cos values and sine values of this element in to represent in y-axis and x-axis. So let us consider a local coordinate system. Let q1 dash and q2 dash with the axial displacements at node 1 and node 2 respectively, and q dash be the elemental displacement. So we can represent this as q dash is equal to q1 dash q2 dash transpose. So similarly, global coordinate system, let q1 and q2 be the x and y displacements at node 1 respectively, and q3 and q4 be the x and y displacement at node 2 respectively, and q2 be the elemental displacement matrix. Thus we will get q is equal to q1 q2 q3 q4 whole transpose. So the relationship between q and q dash is obtained by referring the figure in the previous slide, wherein q1 dash will be equal to q1 cos theta plus q2 sin theta, and q2 dash will be equal to q3 cos theta plus q4 sin theta. So for our ease of understanding and simplification, let L be equal to cos theta and M be equal to sin theta, where L and M are the direction cosines. Thus we can write q1 dash is equal to L into q1 plus M into q2, and q2 dash is equal to L into q3 plus M into q4. So now if I want to write this in matrix form, I can again rewrite this equation in the matrix form. We shall see in the next slide the matrix form of writing this equation 4.35. So here we can see that q1 dash q2 dash matrix is equal to LM0000 LM into q1 q2 q3 q4, or q dash is equal to L matrix into q matrix, where L matrix is called as the transformation matrix, which is equal to LM0000 LM, where L is nothing but cos theta and M is nothing but sin theta. So to find the direction cosines of L and M and effective length of the element LE, so let us refer to the figure 4.8, where x1 and y1 and x2 and y2 are the coordinates of the nodes 1 and 2 respectively, and the direction cosines are L and M, and effective length of the element LC will be given by L is equal to cos theta, that is equal to x2 minus x1 by LE, and M is equal to sin theta, that is equal to y2 minus y1 by LE. So the direction cosines can be written in terms of L and M. So LE, or the length of the element, can further be written as LE is equal to square root of x2 minus x1 square plus y2 minus y1 square. Considering this to be a figure 4.6, considering it to be the Pythagoras theorem, I can write the value of LE in terms of x2, x1, y2, y1. So the value of LE we shall see in the next slide. So here you can see the value of LE is considered from the Pythagoras theorem, which is nothing but the effective length of the element written in terms of x2, x1, y2, y1. So the truss element is equivalent to one-dimensional bar element when viewed in the local coordinate system. Hence the elemental stiffness matrix in the local coordinate system is given by Ke dash is equal to E A divided by L into 1 minus 1 minus 1 1, where AE is the elemental cross-sectional area and EE is the Young's modulus, and elemental strain energy for the truss element is given in local coordinate is given by U is equal to half K dash Q dash into Q dash transpose, where the single prime dash represents the local coordinate system. But we are bound to find the elemental stiffness matrix in global coordinate system. Hence we know that Q dash is equal to capital L into Q. So substituting equation 4.44 and 4.43, we get UE is equal to half L into Q, K dash into L into Q transpose, which is equal to half Q transpose into L transpose into K dash L into Q. So the strain energy in global coordinate can be written once again as U is equal to half Q transpose into K into Q, where K is the elemental stiffness matrix in the global coordinate system. So comparing equation 4.45 and 4.46, we get that K is equal to L transpose into L into K dash, where L is the transformation matrix which is given by L is equal to L M 0 0 0 0 L M. So here you can see U is equal to half QT K into Q, where K is equal to LT Q K dash into L, where L is nothing but the transformation matrix represented by LM 0 0 0 0 LM, or L transpose is equal to L0 M0 0 L 0 M. But we know that L is nothing but cos theta, M is equal to sin theta, which are the direction cosines and stiffness matrix in the local coordinate system. So now let us try to rewrite the stiffness matrix with the direction cosines, So moving to the next slide. So here you can see K dash is equal to E into A divided by L, or AE divided by L into 1 minus 1 minus 1 1, and L dash into K can be written as AE divided by L into L minus 1 M minus M, L minus L M minus M minus L minus M, or K is equal to L transpose into K dash into L, which is equal to AE divided by L into L minus L M minus M minus L minus M into LM 0 0 0 0 L M. So on simplification and multiplication of this matrix, we will get the global stiffness matrix for the truss element, which is represented in the next slide. So here on simplification and multiplication, we get the global stiffness matrix, which is equal to K is equal to AE divided by L into L square LM minus L square minus LM, LM M square minus LM M minus M square, minus L square minus LM L square LM, minus LM minus M square LM into M square. So this is equation 4.48, which gives the elemental stiffness matrix for the truss element in the global coordinate system. So this is the stiffness matrix for the truss element in the global coordinate system. So if we are considering the elemental stress matrix, we know that the truss element in the local coordinate system is equal to one-dimensional bar element. Hence the stress matrix is given by sigma is equal to E into B into Q dash, or E into B into L into Q, where B is nothing but 1 by LE minus 1 1. It is the strain displacement matrix, and Q dash is equal to Q1 dash Q2 dash. So simply writing stress sigma is equal to capital E suffix E divided by L suffix E into minus 1 1 LM 0 0 0 0 LM into Q1 Q2 Q3 Q4. So multiplying this matrix, we get the stress in the element. It is written in the next slide, so we'll move to the next slide. So we get the stress in the element. Sigma is equal to capital E divided by LE into minus L minus M L into M, Q1 Q2 Q3 Q4. This represents the stress matrix for the truss element. Similarly, finite element equation for a truss element with the 2 node. So it is given by F is equal to Ke into Qe, where F of E is the element force vector, which is nothing but a column matrix, K is the elemental stiffness matrix, and Q is the displacement vector. And all three F and Q are the column matrix, whereas K is the square matrix. So it can be written as F1, F2, F3, F4 is equal to L square ML minus L square minus LM, ML M square minus ML minus M square, minus L square minus ML, L square ML, minus ML minus M square, ML into M square into Q1, Q2, Q3, Q4, where K is the stiffness matrix. K is the stiffness matrix. So the reaction forces R at the support for entire truss is given by reaction force R is equal to K into Q minus F, where K is the global stiffness matrix, Q is the global displacement vector, F is the global force vector, and R is the global reaction vector. Okay, so with this we have completed the derivation for the truss element. So next we shall see only problems pertaining to bar element and truss element in the coming videos. Thank you.